I agree.
Okay. Hello and welcome everybody to this week's Infosys-Chandrasekharan Random Geometry Colloquium. Today, it's our great pleasure to have Nicolas amongst us who will talk on Cheeger constant of graphs and surfaces. Over to you, Nicolas.
Thanks a lot, Shubhajit. Thanks a lot. So yeah, the goal is to tell you a few things about some well-known objects, geometric objects, which are Cheeger constant of graphs and surfaces. And this is inspired by a work which I have been doing last year with Thomas Budzinski, who is CNRS at École Normale Supérieure de Lyon, and Bram Petri, who is assistant professor at Paris-Saclay, now Sorbonne Paris University. Okay, so
recording in progress.
I guess that many of you, yes. I hope that many of you is familiar with the Cheeger constant, but I will recap what it is slowly to to be gentle with you. So let's start with the case of graph. So imagine you have a graph. So in my talk, the graphs will always be simple, meaning that I don't have multiple edges linking two different vertices. There will be no loops, just to simplify, and they will be connected always. So that's a graph. And if you have a subset of vertices of your graph, you can define its isoperimetry. So the isoperimetry of your subset A will just be the size of the boundary of A divided by the size of A itself. So what is the boundary? The boundary of A, so your set A is here, is just the edges that have one leg, one foot inside A and 1 foot outside of A. Okay, so that's the boundary of A, which are the edges going out from A. And let's say that the size of A, just the cardinality of A, just the number of vertices, right? So, so that's for the isoperimetry of a given subset of a graph. And let's define now, let's define what is the Cheeger constant of a graph. So the Cheeger constant, I will denote it with an H star just to distinguish it, sorry, from the H. So the Cheeger constant of a graph will be defined in two different ways, depending whether G is finite or not. So if G is finite, it's just the infimum of all isoperimetry of subset A, where A runs over all subsets of your vertices, provided that the size of A is less than the total number of vertices divided by 2. Why? Because otherwise you just take A as the whole graph, and obviously there is no boundary, and so the isoperimetry is just 0. Okay? If G is infinite, then you can just take infimum of all subset HA, so that A is a subset of vertices which is finite. Okay? So let's do two classical exercises. What is the Cheeger constant of, say, Z2? When I say Z2, I imagine the graph Z2 with the standard subset of edges, right? Okay, so in there are easy subset of vertices. Imagine you take, as for A, you just take the vertices, n by n. Just take a box n by n in Z2. And let's compute the isoperimetry constant of this set. So the edges that are going out from A are these orange edges that I'm drawing. So how many edges you have? Okay, roughly n, so it's of the order of n. But what is the size of A? So the size of A is comparable to n squared, because I have n by n box. And so the isoperimetry of A is roughly like n over n squared, which goes to 0. So clearly now you can take bigger and bigger boxes in Z2, and so the Cheeger constant of Z2 is just 0. Okay, so the other example which you have to keep in mind is the Cheeger constant of the 3 regular tree, which I will denote T3. So what is this guy? It's just the infinite tree where all vertices have degree 3. Okay, it goes forever. Okay. Now, if you want to do the same thing here, you can imagine that you take big boxes in T3. So what is a big box in T3? So you start with 3 legs here, 3, 3, 3, 2, 2, 2, up to distance R, let's say. Okay, so let's imagine that you do that for general D. So D will be the degree. So what is the size of this guy? Okay, A is this guy. What is the size of its boundary? So the boundary will have size, what is it? Is it D times D minus 1 to the R minus 1, something like that. And the size of A will be 1 plus D, D minus 1, so on, until D minus 1 to the R minus 1. And here it's an R. Okay, so if you do the ratio of those two guys, okay, maybe I'm mistaken, but you can check that. So this goes to, when R goes to infinity, this goes to D minus 2, which is actually 1. When D is equal to 3, it's 1. So what does that mean here? That means that if you take big boxes in your tree, and you look at the size of the boundary with respect to the size of the inside, then they are roughly proportional, and the proportionality constant is D minus 2 here. Now, easy exercise, this is the best possible. I mean, if you want to minimize this isoperimetric constant of a subset, you want to take balls in a large tree. So I have not made the proof, but I leave it as an exercise that actually the Cheeger constant of the D regular tree is D minus 1. So the infimum of all finite subset in a tree of the size of the boundary with respect to the inner size is this proportionality constant, which is D minus 2. Okay? So far, so good. So we have two types of graph. The graphs which have Cheeger constant 0 and the one which have Cheeger constant strictly positive. And I will be interested in those ones in what follows. So this was the case of, infinite graph. But now I will look at finite graphs. So what do I have for finite graphs? So let's look at extremes of the Cheeger constant over finite graphs. By the way, if something is not clear or if I go too fast or too slow, do not hesitate to interrupt me. Okay, so I will be denoting GD of n, the set of all D regular graphs with size n. So n vertices, and all vertices have degree D. They are finite, they are connected, and no multiple edges, as I say, and no loops, just to simplify. So let's look at the infimum of all Cheeger constant of graphs G, where G runs over this set of graphs GD of n. What is this infimum, and how does it behave when n is large? So that should be very easy, right? The infimum of all Cheeger constant. And I claim that this is 0, that you can have very large D regular graph with small Cheeger constant. Why? Well, just imagine that if you were to take D is equal to 2, you have very large graphs which look one-dimensional. Okay, so that's a graph in G2n when you have n vertices. And if you look at a piece of this graph, a large piece here, which is your subset A, What is the boundary of A? The boundary of A is just made of this point and this point, whereas the size of A can be as large as you wish. So the ratio boundary divided by size goes to 0. You will tell me, oh, but that's very specific of D is equal to 2 to the degree 2. No, it's not. Because if you were to take degree 3, then you can mimic this construction and take something like that. Okay, this graph will have degree 3, and you go on forever. You see what I'm doing? Here it's a large piece. So you can mimic one-dimensional graph with D-regular graph, which look one-dimensional seen from very far, and so their Cheeger constant can be as small as you wish, provided that the graphs are large. So this is 0. This tends to 0 as n goes to infinity. That's very easy. On the other hand, if you look at the supremum of all Cheeger constant of finite graphs, G in GD of n, let's look at this quantity now when n goes to infinity. So there is actually an easy argument which tells you that regardless of n, this is always less than the Cheeger constant of the universal cover. The universal cover of those graphs is just the D regular tree. This is D minus 2. So that's an exercise, and that's easy. It's just when you explore a D regular graph, if you want to have a large Cheeger constant, you don't want to that two edges lead to the same vertex. You don't want further identification, the identification which are in the tree. You don't want further identification than that. So it's a easy argument, and I leave it as an exercise. So this is always less than D minus 2. But how does it behave when n goes to infinity? Okay. So remember this question. We want large Cheeger constant for finite but very large graphs. Now, let me tell you the funny story about this quantity. This quantity, let's, just to be precise, let's define the limb soup of this guy as n goes to infinity. And let's call this h of d. Now, let me tell you the joke. The joke is that in 1978, Peter Boozer, in a paper, conjectured that HD is equal to 0. That actually you cannot build very large graphs which have a positive Cheeger constant. What is funny is that 3 years later, 91, Boozer, the same Boozer, proved that actually HD is larger than 1/256, whatever the constant, strictly positive. So he conjectured it was 0 and proved using a hyperbolic surface that it was strictly positive.
So no matter what the D is.
Yes, it works for D is equal to 3, and then it keeps increasing. So what is really funny is that actually this result was known to Margulis. Margulis proved roughly the same thing back in 73, using roughly the same arguments, hyperbolic surface and so on, using the 3/16 Selberg theorem. So this famous theorem about hyperbolic surfaces. And what was even funnier is that before Margulis, Pinsker had constructed graphs which have this property, also in 73, using probability. Using probability. So what he showed, actually, Pinsker, is that if you take G in this set, GD of n, uniformly at random, then with very large probability, you will satisfy a bound like that. So in particular, there exist graphs with large Cheeger constant. So that's funny, right? But it's what is really funny is that actually in 67, Kolmogorov, the great Kolmogorov, and Bardsdin already proved, kind of hidden in their paper, proved already this fact. So what is this fact? this fact is that there exist large graphs, large deregular graphs, deregular, so that the Cheeger constant of those graphs is bounded away from 0, let's say larger than 1/200 and whatever the constant. And those guys are usually called expanders. Why expanders? Because on them, if you look at processes on them, the processes have a tendency to blow up exponentially. Think of an epidemic. If you start an epidemic on this graph and the epidemic propagates along the edges of the graph, if you have infected a region A by time t, then at time t plus 1, you will infect all the neighbors of A, and the neighbors of A by this property is proportional, at least proportional to what is in A already. So the epidemic will grow exponentially. So these graphs are very, very, very important because they are finite. So it's a finite world, but they have this small world effect. They are very well connected, although their degree remain bounded. The maximal degree remain bounded. Okay, so that's funny because actually Kolmogorov and Budzinski, for the little story, they were not interested in building expanders, but they were interested in the size of the brain. So let me tell you that story because I think it's funny. So they were interested in size of the brain. What was their observation? Their observation is if you look at a brain, a real brain, I mean, the cells, the neurons, the cells, they are on the boundary of the brain, and what is inside the brain is just the cables, the axons, all the cables or the edges. And they were asking the question, what is the volume growth of a brain with respect to the number of cells? Okay, so what is a brain? Let's say that a brain is made of cells which have diameter 1, whatever the unit, and they have edges which also have diameter 1. Okay, and they are 3 regular, let's say, to simplify, and they connect. And of course, these are real cells, meaning that 2 edges cannot overlap in 3 space, in R3. Okay? And now you want something very connected, right? You want a brain that functions very well. And so you want that the connection between neurons are fast. And so you will build a graph like that. Gn will be your brain, and Gn will be an expander. Right? And so what they proved is that actually the volume, the real 3-dimensional volume of a brain with size n actually grows much faster than n. And of course, because if you have n cells and they have diameter 1, they occupy a volume of, say, 1 unit, you multiply by n, so at least the cells, they will occupy a very large volume. But actually, they prove that this is some constant n to the 3/2. That means that if you have n cells and they are very well connected like an expanders, most of the volume of your brain will be made by the cables, not by the cells. Exactly as in our brain, if you look at the brain of a human being, you see the gray cells on the boundary, and most of the volume of the brain is actually made of the cables of the edges, by the edges. Okay, so that's funny that biology actually created this field of expanders. Okay. Questions? So now let me recap and tell you that there is actually a strict inequality. So what is HD? HD is the lim sup of the Cheeger constants of large graphs. We said that HD is less than the Cheeger constant of the deregular tree. And we said that this is larger than 1/256. But what is HD? So I will not tell you what is HD because I don't know, but I will tell you a funny theorem due in its first form to Bollobas and then sharpened by many, including Alon and so on. So what they prove is that actually this inequality here is strict and much more than strict. HD is less than D minus 2, but divided by 2. So you cannot, using finite graphs, attain a Cheeger constant, which is the one of the tree. And by much, I mean, you must stay below half of the Cheeger constant of the tree. Okay? So in finite world, there is no way you can approach this bound here. Okay, so let me tell you the proof because the proof is very nice and in a sense, ridiculously simple and brilliant idea. Okay, so fix a graph, Gn, D irregular, size n. Your goal is to prove that its Cheeger constant will be less than D over 2 minus 2, D minus 2 over 2. How? So what do you want to build? You want to build goal. You want to build A inside Gn with a small isoperimetric constant. Okay, the isoperimetric constant, small. But you don't know anything about your graph. Your graph can be virtually anything. So how will you build A in a clever fashion? Well, the idea is just to take A at random. Take A inside the vertices of Gn, uniformly at random. So what I mean uniformly at random, let me be more precise here. Any vertex will be colored white or black with probability half. Okay, so for every vertex of your graph, you flip a coin, fair coin, independently to color black or white. And then you take A, all the black vertices. Okay? So what is the size of A? Well, you had n vertices, you color them independently with probability half, so the size of A is roughly n over 2. You agree with that? It's very concentrated, it's a law of large number. What is the boundary of A? So the boundary of A, you have to believe me as well here, it's very well approximated with the expectation of the size of the boundary. And the size of the boundary, it's very simple. You sum over all edges of your graph of the probability that your edge is in the boundary of A. But what does that mean for an edge to be in the boundary of A? Well, it's very simple. You must have 1 foot black and 1 foot white. So you must be bichromatic, like that or like that. So what is the probability for one edge to be bichromatic? It's 1/4 plus 1/4. It's a half. Okay? And how many edges you have in your graph? Well, you have n vertices, recall, and every vertex has degree d. So if you have d times n, that's the number of edges that you counted twice. Because if you count from every vertex the degree, you will count every edge twice from the 2 endpoints. So the number of edges here is dn over 2. So in total, you see that the boundary of A is like dn over 2 times half, which is roughly dn over 4. Okay? You recap. What is the Cheeger, the isoperimetric constant of A? It's dn/4 divided by n/2. And this gives d/2. It's not quite what I wanted, but very close. I wanted d-2/2. But already d/2, it's already quite nice because already d/2 is less than d-2 for d large enough. Let's say for d larger than 5, it already works. Okay? But let's do the real proof. How can I get now? My goal now is to get an additional -2 here. So I need an additional idea, and the additional idea will be to be a little bit more clever before my coloring. So the additional idea is to, before coloring, to split the graph GN into packet. Renormalization, if you like, if you like percolation or whatever. What do I mean by that? I mean that you have your graph GN. You just want to split your graph into packets which are large, but not too large. So this packet will be denoted by C1, C2, like component 1, blah, 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 up to component K. What do I want? I just want that CI is a graph connected. And I want that the size of CI is large in front of 1, but small in front of n. Okay? And I claim that this is very easy. There are many ways, many deterministic ways to do that. For example, you start from a spanning tree of your graph, and then you cut your spanning tree into packets, satisfying those properties. This is easy. Okay, so you do that on G, and then you color. Each packet, CI, will be colored black or white with probability half. So that means that once you did your renormalized graph with your packet, then you will color this one black, then white, black, and black, and that's it. Okay? And then you take the same thing. A is made of all the blacks. Okay? So let's do the same calculation as before. What is the size of A? Well, the size of A, you have many packets. Each packet is large but small compared to n, and you color them with probability 1/2 in black and 1/2 in white. So you should be convinced that roughly the size of A is roughly the size of your graph divided by 2. So this is n/2. Now, what is the size of A? Again, you have to believe me, here it's concentrated around the expectation, and the expectation is the same thing. You sum of all edge, that's the probability that your edge is in A.
By the way, so in A, you are not just saying number of like the black packets, rather all the vertices covered by them, right?
All the vertices, the vertices.
Yeah, okay.
Let me be clear, very good question. Let me be clear here. It's all the vertices, okay, vertices belonging to CI, and CI is black. All of them. It's all the vertices here. Okay? Okay, we already computed that, right? Because if you have an edge and you want it to be bichromatic, you want that this one falls in some packet CI, that this one falls in some packet CJ, and the color of the packet should disagree, should be black, white, or white, black. And this probability is 1/4 to be white, black, plus 1/4 to be black, white, which is 1/2. But we're doing the same calculation, right? What has changed here? What has changed is that if your edge is already inside a packet, then you know that it will be monochromatic. So here, the edges, you will not sum over all edges of your graph, but you will only sum over edges between packets. So that's the edges which are in between two packets, two Ci, Cj. That's the only thing that has changed. Okay, so how many edges do I have? Recall, I have my graph here, which is cut into packets. And I said that the number of edges of your graph, the total number of edges, was dn/2. That's the total number of edges. But what do I want to subtract? I want to subtract the edges which are inside the packets. Okay, all those edges, I know that they will be monochromatic, either black or white, like that. But inside the packet Ci, how many edges do I have? What do I know? I know that the guy here is connected. So I know that the number of edges, let's say Ei, is bigger than Ci minus 1. Because on a graph with n vertices, if I want to be connected, I need at least n minus 1 edges. Very simple. And so the sum of all Ci's of the number of edges of the packet Ci, this is larger than sum of the size of Ci minus 1. So this is larger than n minus k. K is the number of packets. But the number of packets, recall, I said that the packets are small, but not too large. Are large, but not too small. Sorry. They are large, but not too small. They are large, but not too large. But since they are large, the number of packets should be small o of n. There cannot be many, many packets, because if you have many packets, some of them will be small. So k is negligible in front of n. Okay? So now if you sum over all these edges here, this is at least n dn minus 2 minus, at most, sorry, minus n. And this is exactly the d minus 2 that you wanted over 2 times n. And now you do the same argument as before, the argument that was here. And you will get the same result with the d minus 2. Okay? Are we good? So.
Can I ask a question?
Of course.
So this theorem by Bollobas, we are proving it for finite graphs, but is a similar result true for Cayley graphs for finitely generated groups?
Finite Cayley graphs or infinite?
Infinite finitely generated groups, yeah.
And so where is the theorem you have in mind, that the Cheeger constant of quotient of those guys? Because
no,
here,
I was just thinking Cayley graph of a infinite group, which is still finitely generated.
Yes.
And then if let's say I fix the number of generators, and I look at the lim sup over,
yep,
something like that.
I don't know. So okay. Here you want to replace the tree TD by one infinite Cayley graph, and those graphs G and D by all finite quotient of those graphs, and you want to.
I guess that's a better question than what I was thinking. Yeah.
Let's build on this question.
Yes.
So you want to ask whether the supremum of the Cheeger constant of those finite quotient of an infinite group could reach the Cheeger constant of the group?
Yeah.
I don't know, but good question. I don't know.
Thank you.
I have a question.
Yes, sure.
Yeah, so instead of looking at the set GDN, what if we look at the graphs which only have a uniform degree bound of D, let's say, with size n? Then the same bounds, etc. work, right?
Yes, so you want to relax the condition that they are d-regular by bounded degree?
Yes.
It works the same.
Yeah. Okay.
Yeah. But let me tell you how much I am ignorant. So what have we proven so far? Let's recap. We have the maximal, okay, the supremum of a Cheeger constant of a finite graph for large graphs. We know that this is less than d minus 2 over 2, which is strictly less than d minus 2. This is the Cheeger constant of the d-regular tree. And we know it's larger than 1 over whatever. But H3, I don't know what it is. Nobody, not that I know. H3, this number H3, the maximal Cheeger constant over 3 regular graphs, for large n, I don't know. H4, what is exactly? So what we know is that HD, when d goes to infinity, will tend to d minus 2 over 2. And we have also rates. But this is already very, very cutting edge research. But H3, we don't know. And we don't know what are the graphs that should maximize the Cheeger constant. Are they Ramanujan graphs? I don't know. Okay, so now let me tell you part 2. Let me tell you what we are after. We're after hyperbolic surfaces. So what are hyperbolic surfaces? Well, if you want the take-home message, everything works roughly the same as for graphs. So what is a hyperbolic surface? A hyperbolic surface is a constant curvature Riemannian manifold. The curvature is constant equal to -1. I will only take closed surface, compact even, so that they are classified by their genus, which is the number of holes, which is just belonging to 0, 1, 2. So it's...
Sorry, I have a question. Sorry to interrupt.
Yeah. I will be down to earth in a minute. This is the, yep. But please.
Yeah, I had a question about the, I mean, inspired from the proof. So basically, can we say that if you fix some epsilon greater than 0, then for very large d, the graphs in GDN for which your HD is epsilon close to d minus 2 upon 2,
yes,
have clusters just like the ones in the proof?
So
I mean, they have.
It's not what I've said, but what you're saying is correct. So actually, the probability that if you take a graph GN uniform, take a graph GN uniform in GDN with large d, the probability that its Cheeger constant is larger than d minus 2 over 2 times, say, 1 minus epsilon, because this also grows with d. Let's say lim-sup, lim-inf of this probability as n goes to infinity. Well, this number depending on d only, tends to 1 as d goes to infinity. So in words, if d is very large, not only there exists graphs which have a Cheeger constant which is close to d minus 2 over 2, but actually most graphs will have this property, that if you take a graph uniformly at random, then actually its Cheeger constant is roughly d minus 2 over 2. Does it answer your question?
Also, do they also look like, as far as their connectivity structure is concerned, do they also look like chopping up your graph into these compartments? And
no. This
okay.
was this. It's a very, very nice question because usually the probabilistic method here the probabilistic method enters twice, not in the proof. The proof, it enters only once here because I'm just coloring a fixed graph. The graph is not random. I want to prove that for a fixed graph Gn, there exists some subset, blah, 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 A, blah, blah. So actually here, the probabilistic method picks a random subset of a fixed graph. And this allows me to upper bound the Cheeger constant. Yeah. Okay? But actually, the probabilistic method enters from another door if you want to have a lower bound on the Cheeger constant. Remember the question of Boozer here? Boozer was wondering 40 years ago, was wondering whether you have graphs with large Cheeger constant. And here, if you take a random graph, then actually the Cheeger constant of this guy is bounded away from 0. So the probabilistic method now enters by picking the graph at random. And it gives a lower bound. So it's one of the only instance where that I know where the probabilistic method enters for the upper bound and for the lower bound. But you see that the randomness is not located in the same place. It is on the graph for the lower bound and on the subset for the upper bound. Does it answer your question?
Okay, yeah, I got some idea. Thank you. Yeah.
Okay, so hyperbolic surface. So those guys build like that. But actually, there is a very easy recipe to build hyperbolic surface from graphs. They are built from what we can call, what is called pen decomposition. So what is a pen decomposition? It is a decomposition of your surface into pairs of pens, exactly as I am drawing here. You see, I'm drawing pairs of pens, like trousers, and they are glued together according to some combinatorics, provided that you have some length on your trousers. Let me finish it up. This one is not that nice. Okay. Imagine that these are actual trousers, two-dimensional guys, and they have a length here, A. And if on the opposite side I have the same length A, then I can sew them together. And the fact is that there is a unique, well-defined hyperbolic pair of pens for each triplet A, B, C, which are the length of your 3 holes. Okay? And so, fact, a hyperbolic surface can be built by taking a trivalent graph that you see here. You see the trivalent graph with vertices being the pens and edges being along the length of the pens. So you have a trivalent graph, Gn, and what you need on top of that, you need those coordinates, which are the length of the belts, let's see, of the pens you want to glue. And there is an additional coordinate, which is the twist, the angle you may turn your trousers before sewing them together. Okay? So actually, once you do that, you have mg. So what is this? This is the isometry classes of hyperbolic surface, which are compact with genus G. This plays roughly the same role as our space GD of n of all D regular graph. D here, you may think of it as fixed, and n plays the same role as G. So this space is nice. It's not a discrete space. This one was discrete. It has a finite number of elements in it, but this one is almost as nice. It's a compact, finite dimensional manifold. So it's the continuous counterpart as to finite set. Okay? And now you can do exactly the same for hyperbolic surface as for, yes? Yes?
Yeah. Quick question. So for this moduli space, are you normalizing the Pantz curves to lie
No.
in some length bounded away from 0 and infinity?
No.
No.
No. All lengths are allowed, but actually, but actually,
yeah. But you're saying something about the cusp. I mean, the volume near the cusp is small. Is that? I mean, I'm a little bothered about this compact
any volume. I'm not taking any measure yet on MG. I see that as an abstract space with no measure in it. Let's say all isometric classes of hyperbolic surface of genus G, not endowed with whatever. I'm not speaking about that. Okay?
Okay.
Is that okay?
Okay. Yeah. So the other thing is that quotienting out by the isometries, right? So I mean, essentially,
if Nielsen, I'm quotienting.
Okay.
I'm not taking the I'm not on the Teichmüller. I'm really on the moduli space for the experts. Yes. Okay. Now, same questions. If you have a hyperbolic surface, and if you have a subset A of your hyperbolic surface, you can define what is the isoperimetry of A. The isoperimetry of A is the length of A. What is the length of A? Well, it's the one-dimensional length of the boundary here. And what is the size of A? The size of A is the hyperbolic area of A, which is well defined because I have a Riemannian manifold with constant curvature -1. So it has a well-defined area measure. Okay? And if I have my surface, S, what is the Cheeger constant of S? Same definition. It's the infimum over all H of A, where A is a subset of S, whose size is less than the size of S divided by 2. All right? Same definition. But notice a fact that is very different and which is annoying, very different from the graph case, is that here there is no upper bound on the size, on the boundary of A. The boundary of A may be fractal. If you take A like that, then this could be infinite. Why not? Okay, same question. What is the limb sup when G goes to infinity of the Cheeger constant of a hyperbolic surface SG, where SG lie in the moduli space MG? We're interested in that. Same story. Boozer, Pinsker, or not Pinsker, but let's say Boozer, Margulis, and so on. They tell you that this is more than, let's say, some positive constant. So this is the existence of expander graphs or expander surfaces. And same story, this is less than H of the hyperbolic plane, which is the universal cover, which plays the role of the tree, hyperbolic plane. Let me denote that by H star of hyperbolic plane. And this is just 1. This plays the role of my D-2. Okay, and the theorem I want to state with Thomas and Bram is that actually we also have a strict inequality here. What we prove is that, let's call this guy H. Well, we prove that H is less than 2 over pi. And 2 over pi, by the way, is strictly less than 1. Okay. I still have 5 minutes, right?
Actually, I think like 10 minutes. Yeah.
Good. Okay, so even if you're not familiar with hyperbolic surface and so on and so forth, try to hang on, because there are some nice geometric facts, very aesthetic, that will come in a few minutes. So let's start the proof. And let's try to mimic exactly the proof of Bollobas. So you have your surface, SG, which is given. What is your goal? Your goal is to find A inside SG with a small isoperimetric constant. You know nothing about SG. So how will you pick A? In the graph case, the first idea was to color all the vertices black and white. You cannot do that on a continuous surface. Can you color all the points of this square black or white with probability half? There are uncountably many points. You cannot do that. You cannot color all the points of the real line black or white with probability half. Well, actually, you can, but then it's not a separable probability space. It's not standard probability. It's really, you must be cautious. So how can we fix that? Well, think about the second idea of the proof. The second idea of the proof, or the second round, was to first divide your surface into packets. But here, I said that in the graph case, there are very easy deterministic ways to cut your surface into packets. Not here. Here, we need to use probability again to cut your surface into packets. So what is the idea? The idea will be to, in your surface, to cut it into packets using random points. So what you will do is you will sample lambda. Lambda will be small, tending to 0. Lambda times the size of your surface, points. Okay, so you have points. If lambda were 1, if it were 1, that would mean that for every unit area of my surface, I have 1 point, roughly. But since lambda is small, that means that I have very few points compared to the area. And now what I will do is my packets will be the Voronoi cells associated to this Poisson process, So what are the Voronoi cells? So the Voronoi cell is the points which are closer to one given point than the others. Okay? So it's the basin of attraction, if you wish, for the distance of those points. So in something like that, I don't know. Let's build something easy. Okay? These are those.
Sorry, Nicolas, probably missed it. So you take a Poisson point process, intensely, or?
Yes, so it's the same. Here, to simplify, I said I sample a fixed number of points, but in the limit, when G goes to infinity, it's the same as sampling a Poisson process with intensity lambda, because the size of my surface, not the area of my surface is this big as G, and it's large, and so it's the standard Bernoulli Poisson approximation. So that's the same. Okay. So now I want to see how does it look like, and for that, let me show you what it looks like first on its universal cover on the hyperbolic plane. Okay, so let's do that. And I should have something prepared here. I share my screen. Up. You see that?
Yeah.
You see the diaporama here, the pointless Voronoi tessellation, you see?
That's right, yeah.
Perfect. So this is a Poisson process of intensity lambda, where lambda says 1, in the hyperbolic disk represented in the unit disk model. So you see the points, and you see that each cell of a point is the points which are closer to this one than any other points in the tessellation, right? Now, if I diminish the intensity, so if I let the number of points per unit area goes to 0, I have fewer and fewer points. You see that? But I still have well-defined cells. And what is very funny.
Sorry, Nicolas, are we supposed to see some animation? Because
no.
Oh, no. Okay, that's okay. Fine. That's okay. I just wanted to.
Sorry. You have high expectancies with my too high. So I diminish the intensity, let's say step by step. So there are fewer and fewer points. And in the limit, when lambda goes to 0, you don't see any point anymore. But what you still see are the interfaces of those Poisson Voronoi cells. What I mean is that if lambda is really tiny, like 0.0001, the first point here, the first point that you will see.
Sorry, Nicolas, to disturb again. I think we're not even, at least I'm not seeing the slides. I think probably I'm still seeing the first slide, which just says the pointless Voronoi tessellation.
Yeah, same here. I only see the title slide.
Sorry. Let me start. Okay. You see now?
Yeah, you see the hyperbolic disk, I think, kind of.
Okay.
Yeah.
And now let me diminish the intensity. So I have fewer points. And now let me diminish until 0. And I don't see any point anymore, but I still see the interfaces between those points. So those points, if you wish, are very far away at infinity, but actually the frontier of those Voronoi tessellation, they still come close to the origin. The origin is right in the center. Okay?
And by the way, here the boundaries are like the hyperbolic geodesics or what?
Yes, exactly. And this is the object that is underneath the proof. So what we need to prove, our main theorem, is that actually the tiles here, all the tiles, which are random objects, all the tiles, they have a Cheeger constant, if you wish, which is 4/π. So the ratio between size, boundary size and area for these tiles is 4/π. And once you do that, then you do the coloring, and the coloring will cut by 2. Exactly. Then the rest of the proof is the same. So from the 4/π, you will get to 2/π, which is the constant here. So that's calculation with stochastic geometry. And actually, this is a calculation that was performed long ago in the beginning of the 2000 years by Isokawa, a Japanese. We need to trick it a little bit, but this is the object which is underneath the proof. And just to finish, let me show you the analog of that in 3D. I mean in a 3-dimensional hyperbolic space. So you will do the same. You will take points on the hyperbolic ball in 3D. You will let the intensity goes to 0, and you will look at cells. Of course, I cannot show you the whole picture, but let me focus on one cell. Say the cell containing 0. So this cell looks like something like this, which is an hyperbolic polyhedra, where the faces are hyperbolic polygons in 3D, and which have here, there is a boundary effect I need to cut at some point, but it has an infinite number of sides which accumulate only at one point. It has one end. So you need to imagine that those cut ruby are glued together and that they form the whole hyperbolic 3 space. So these objects are objects we're now studying with Meltem Unel, Matteo D'Achille, Nathanael Enriquez, and Russ Lyons, based on the work I just presented. I think my time is up. hope I have cheered you up, and thanks a lot for your attention.
Okay, let's thank Nicolas for this wonderful talk. I think we can take probably a few questions. Nicolas?
Yes.
Could you say what's the statement in the 3 dimension? Like what would be the theorem you're working on?
So the theorem in 3 dimension, I'm not interested in Cheeger constant anymore. I'm just interested in the in this phenomenon, which is the fact that for hyperbolic space, if you take a low intensity Poisson process and you let the intensity go to 0, then it converges towards a tessellation here, which is a tessellation of your plane where the ties are now infinite polygons. You see, they're infinite. They have, and we study those guys. So it is
like the isoperimetry for those.
Yes, isoperimetry for those, and we compute the law of those guys, various constant like the isoperimetry, the number of points, the whole probability, what is the typical distance of a point to the boundaries, things like that. So yeah.
So just in this connection, for example, if I try to draw a naive analogy, the random planar maps, you'd like to study, let's say, I don't know, the diffusive constant of the random walk or some diffusion process on this, or
on this one. I think you can, but we're starting even with more basic properties than that.
Yeah, sure.
Just defining the objects and studying.
Yeah. No. Even making sense of it. Yeah.
Of course, next step is to understand percolation and so on.
That's right. Yeah.
Actually, low intensity percolation on Voronoi tessellation here has been studied 1 or 2 years ago by Tobias Müller and somebody else. I don't remember.
I see. And by the way, so this constant 2 by pi, I mean, it is kind of, do you believe that is kind of the optimal, like d minus 2?
No, we were happy to prove that there is a gap between, it cannot be 1.
Yeah.
Because this was the conjecture and this was open for 20 or 30 years. But no, 2 over pi is no way the optimal.
Okay.
So the volumes of these is going to infinity, right? As lambda goes to 0?
Yes, the volume goes to 0 like 1 over lambda. Well, the area goes to 0 like 1 over lambda, and the perimeter, the 1-dimensional length, goes to 0 like 4 over pi times 1 over lambda.
You mean like goes to infinity?
I see.
Yes, goes to infinity as lambda goes to 0. It goes like 1 over lambda, but the constant in front of 1 over lambda is 4 over pi.
So, here's the thing. I mean, so you look at the collection of points on the boundary circle to which this Poisson point process converges to. It seems as if, I mean, you're doing something like a random Boussemann function, and then you're looking at a common level set.
Exactly. Yes.
Okay.
Yes. So the setup is you take a point on the Gromov boundary or the Boussemann boundary, but you also need to add a delay. So it's the Boussemann boundary decorated with R, which is the delay of those points. And then from Boussemann boundary cross R, we can build those guys. Here.
I see. Fantastic. Okay, great. Thank you. Yeah.
Okay, if there are no further questions, let's thank Nicolas again for this wonderful, instructive talk. Yeah. Thank you. Thanks a lot, Nicolas. Yeah.
Thanks.
Yeah. We would have very much loved to have you here in Mumbai next year, but okay, we'll try to have you some other time.
Catch me if you can.
Okay.
Thanks a lot for the invitation.
Yeah, thank you. Okay.
Have a nice evening.
You too. Okay. Have a great afternoon. Bye, Nicolas. Bye.